Unread message.
Megan, can you mute your mic?
Okay, trying to look who's the source of the noise. Okay, so chemistry, can we say, is divided into these fields. We have organic chemistry, which is, if you're going to look at the organic chemistry, this is not only the study of carbon, okay? Because as I've told you before, carbon dioxide, it has carbon, but it's not organic, it's inorganic. So if it's an organic chemistry, it's anything that studies carbon containing compounds that include hydrogen. So carbon and hydrogen containing compounds. So you need to have the hydrocarbons as what we call materials in your organic chemistry. Inorganic chemistry studies all the elements in the periodic table except carbon. Now, physical chemistry tries to explain the behavior of the material stuff, while biochemistry look at the biological structure or biological materials at the atomic level. Okay, so the last that we have here is analytical chemistry. Now, if we're going to look at the definition of analytical chemistry from the Working Party on Analytical Chemistry of the European Federation of Chemical Societies, it's defined as a scientific discipline that develops and applies methods, instruments, and strategies to obtain information on the composition and nature of matter in space and time. Okay, so that's just one formal definition of analytical chemistry. Another definition of that is it's a metrological discipline that develops, optimizes, and applies measurement processes intended to produce quality biochemical information of global and partial type from natural and artificial objects and systems in order to solve analytical problems derived from information needs. Okay? So if you're going to look at the word analytical, so that's the basis of the term analysis. Okay? So whenever you involve what we call analysis, that is covered by analytical chemistry. Now, one book describes it as the science of extraction, identification, and quantitation of an unknown sample. Okay? So if you want to determine the composition of your sample, you have to do analytical chemistry. Okay? So extraction, you remove your target material from your sample, and then you identify them, and then you determine the amount. So analytical chemistry also deals with the methods for determining the sample or the chemical composition of the sample. Now, if we're going to look at the two aims or objectives of analytical chemistry, okay, we could say one of them is the obtainment of as high metrological quality as possible. So what does it mean? You want to determine as true as possible the analytical information with as low as possible uncertainty. So you want to determine how much of the material, okay, that you're interested, how much of it is in a given sample. And in addition to that, the other aim of analytical chemistry is to solve analytical problems derived from biochemical information needs posed by clients engaged in a great variety of activities. So this is the routine chemical analysis. Okay? So you will see analytical chemistry is around us. Okay? So what do you mean this client? So health, when you go to health, when they ask you to do blood works, what are usually that they want to obtain there? Okay, last Friday they took my A1C. Okay, A1C is related to what? The sugar level. Okay, so aside from that, you can get the sugar level every day if you're diabetic. So those are the stuff. If you have your urine being analyzed, sometimes they look at the calcium content. Now, in general and agri-food industry, what do they usually analyze or screen here? For toxic materials like salmonella or E. coli and other stuff. In the environment, if you go to Flint, Michigan, they try to determine the heavy metal level, especially lead. So that is done by analytical chemistry. So usually chemistry, okay, or science as a whole, they have four purposes. Okay? Four purposes and sometimes uses. So there are sciences or chemistry that try to explain materials by developing theories. That's where PChem is. Now there are some sciences or chemistry that tries to prepare new compound, and it's something to do with synthesis. Okay, if you want to prepare a compound that has a biological property, but for you to extract it, you need what? 1,000 progs. So all you need to do is find the structure of that material and synthesize it in the lab. Or for instance, the applicability of what? Vitamin C. Instead of drinking or eating a lot of citrus fruits, all you need to do is find the structure of vitamin C and then synthesize it in the lab. So that's the function of synthesis. And because of this synthesis, it's easier to prepare materials that are usually at low amount in nature, okay, by just preparing them in the lab. And then you also have applications. So once you synthesize, you can apply that material that you prepared. Okay? And the last part that we have here is analysis. So you want to determine the amount of a certain material. So you do analysis. And that's where analytical chemistry comes in. Okay? Now, if you're going to look at the analytical chemistry, it covers both internal and external interface. So when we're talking about internal interfaces, it has something to do with the other chemical field, like the one that I have discussed to you earlier: organic, inorganic, physical, biological, and you can also include applied chemistry and engineering, chemical engineering. Now, when we look at the external interfaces, so it has something to do with the other scientific and technical discipline. Remember, we call chemistry as what? Central science. Okay? So other disciplines like biology, biochemistry, mathematics, physics, and engineering, where analytical chemistry can play an active role. For instance, you can determine the enzyme activity or the drugs of abuse in biological fluids. Right now in forensic science, there's always a problems of these new designer drugs. And I don't know if you heard the news 2015, when there's some zombie-like phenomena, when some people took this, I forgot the name, AK-47 gold something, okay, in Brooklyn. And the one who took it become like zombie, okay? So that's what we call the way to analyze those stuff are being done in analytical chemistry. or it can play a passive role, like in the chemometrics development for data processing or the use of immobilized enzyme in analytical process. So if we're going to look at the interfaces that the chemistry play, analytical chemistry play, these are, we could say, the way we're going to look at it. So this is with the other chemistry, and this is with the other scientific discipline. Or the way I try to look at it is here, okay? As analytical chemistry is being related to other science branches. So geology, biology, chemistry, physics, engineering, medicine, material science, social sciences, agriculture, environmental sciences. So these are just some, and I will discuss some of these role that they have. Okay? So it plays a vital role in all sciences, just to name a few: chemistry, biology, biotechnology, forensic science, food science, material science, medicine, and environmental science. When the human genome was sequenced, okay, they call it the breakthrough of the century. Because of that, they now try to develop some therapeutic solutions to inborn diseases. Because by knowing the human genome, they can predict what's the problem in your body. Okay? So the way that they analyze that thing is they use capillary electrophoresis. In the determination of pollutants, okay, analytical chemistry also plays a role. And I have here some specific example. In medicine, as I have told you earlier, if you want to do blood works, okay, analytical chemistry is the basis for clinical laboratory tests which help physicians diagnose disease. So usually if you have what? The strap, they swab your nose, and then they try to culture it, and they try to find if you have your biological organism there. Now other stuff, they try to screen your blood, and they try to see if the levels that you have there of some stuff is within the normal level. Okay? And the good thing in medicine is everything right now is so easy. They become so routinary. Okay? But before they develop that clinical diagnostic thing, it undergoes some major development. Sometimes it took them long time to develop a certain method or assay. In the industry, the analytical chemistry provides the means of testing the raw materials and assuring the quality of finished products. Okay? So maybe we could explain here the food industry. Have you asked yourself what those numbers in some of the foods, like your soda, your cheese? So if you're going to look at the product, there are some numbers there that to you means nothing. But for the one who owns those products, it means something. So usually it's batches. So if ever they do this routine quality control, they will find out which product is questionable. And by that number, it's easier for them to recall which product is defective. Okay? So the food industry is the one that I'd make an example, because that's the one that will affect us all.
Is that how they do recalls, when they recall like a certain food?
Yep. So all they need to do is whenever they produce a batch of these products, okay, some of these they will analyze for QA, quality analysis, and QC, quality control. Now sometimes the product is already out before they be able to get the results. So once they get the results, they validate it, and when they found out that the product is defective, what they do is they're going to do a recall. Okay? So it's usually a standard operating procedure in the industry. Okay? The same thing that happens like in cars. Although chemistry is not involved there, but the way that they do this so-called quality control is similar to what is being done in analytical chemistry. Okay? Now, in terms of environmental quality, so they determine the air in the city to see if there's what? Carbon monoxide. Later on, I will show you a way to determine the water in your place or what they contain. So if you're going to ask yourself which is safe, the water from the faucet or this what we call bottled water, I can assure you, okay, that those water in the faucet before it's being released by the wastewater treatment plant, it should meet a certain guidelines. Okay, unlike the bottled water. The bottled water, they don't have to follow any regulation. Okay, now the only problem is the connections from the wastewater plants to your faucet is questionable. Some of them are so old, so as you could see, most of the water system is made up of what? Metal. Okay, so metal with water, it will corrode. There will be oxidation that will happen. And sometimes the best way that they do is they try to treat it. So what happened in Flint, Michigan is the state tried to save money. So they ship the source of the water from one that is clean to one that is polluted. And even though they treat, okay, it make it worse. It reacts with the water, with the materials that you have in the five, and some of the materials has lead, leading to the leaching of the lead in the water. So right now, as we have said, environment will continue to deteriorate, and unfortunately, the present administration rescinded some of these environmental regulations that was put forth before by the Obama administration. Okay, so before, you cannot just dump your waste in any bodies of water, but they deregulate that executive order, and right now any industry can dump their waste in any bodies of waters. And how do you determine the quality of, when I say environmental quality, so it has something to do with soil, the bodies of water, and the surroundings around us like air. So analytical chemistry plays a very important role on that. And then in terms of forensic analysis, the example that I told you is that proliferation of the so-called designer drugs like K2. Okay. So before they have just to contain with what? Heroin, cocaine. But right now, what do they do? Okay. They try to synthesize new stuff. They still have some of the structure, but they change certain part of the chemical structure that makes it what? More potent. And at the same time, you don't know what will be the long-term effects of these drugs in what we call human beings. So what's the problem, right? The so-called fentanyl, right? So what the forensic analysis is trying to do is they try to develop method to screen them because they never have a method like that. So once a designer drug is being produced, so there's a new method that you can develop. So this is analysis related to criminology, for example, the fingerprint detection and blood analysis. So those are just some analytical chemistry application. Now, there are two types of classification of analysis. There are two ways to classify. Either the qualitative analysis, which answer the question, is it present, with yes or no, okay? Or we could say it determines the chemical identity of the species in the sample. So you could just say, is this chemical present, yes or no? But if you want to determine the amount of that chemical, okay, you're going to do quantitative analysis. So quali is just a yes or no answer to the question, is this chemical present? Quantitative answers the question, how much of this chemical is present? Now, usually, when you do quanti, you still have to do the qualitative analysis, okay? Because some of these quantitative analyses are expensive. So what's the use of doing it when in the first place that chemical is not present? So the first thing that you do is you have to establish first its presence. And then once you establish its presence, you analyze it to determine the exact amount. So in order to perform quantitative analysis, typically one needs to complete a qualitative analysis. One needs to know what it is, and selects the means to determine the amount. Now, there are two types of methods that we have. One that is called classical methods. They usually call this the wet analysis method. Okay? And the other one is the instrumental methods. So this is what they call a modern method. Now, when you have a classical method, you only use chemicals for separation, such as precipitation, extraction, and qualitative analysis by color, odor, or melting point. So let's say you want to determine a certain material. So all you need to do is add a certain chemical. So for instance, if you want some home-based experiment, you want to determine if starch is present. So what homemade material that you're going to use? One you can find in your cabinet, medicine cabinet. You can use your betadine. Okay, so your betadine has iodine. So when it reacts with starch, it's going to form a blue color. So if it's just betadine, it is brown color. So that's just determining the presence of starch. Okay, but the classical methods that you're going to usually do to determine the amount of the material is either gravimetric method, where you measure the mass. We're going to discuss this in later slides, and volumetric method, where you're going to measure the volume. The volumetric method is just your titration. Okay. Now, classical method is the one that is commonly used before 1950s. By 1950s and beyond, some instruments were developed. Okay, so instrumental methods, they use an apparatus to measure physical quantities of the analyte, such as absorption, fluorescence, or conductivity. Okay. Some of the fields that they have in instrumental method: spectroscopy, that look at the interaction of your material with light or electromagnetic radiation; chromatography, which involves separation process; and electrochemistry, that involves current and voltage. So what example that we can use between a classical method and an instrumental methods? Pregnancy tests. How do they use pregnancy? How do they do pregnancy tests before? Before they have that what we call kit that they have right now. They have the so-called prag test. or the rabbit test. So they get a urine sample and they add it and then see if what we call is going to react. Right now, all you need to do is a drop, okay? And if it's what, 1 line or 2 line, it will give you positive or a negative, okay? And they also do it with routine drug tests. Why do you think who's that? Lance Armstrong was able to what? Win a lot of these. What's that? Tour de France cycling. During that time, okay, he was able to how do you say it? He was able to cover up his stuff that he's not using any PED, performing enhancing drugs. Okay, but what happened? Okay, the doping that he did. What happened? They hide the samples. They keep the samples that they have, and once they develop a much better method, which lower detection level, they were able to find that is what? Juice, as they call it in baseball, right? There's a lot of people in baseball that they caught using this PET, including some Yankees player like Aaron. Okay, so this instrumental method is continuing to develop itself. When I say continue to develop, it's trying to improve its detection level. Okay, so maybe during the time that Lance Armstrong was using PED, they still don't have any instrumental method to detect because they still don't know what are those drugs, but they were able to keep some of the samples. And they found out that, okay, he's using some of these PED. Okay, so if you're going to look at these methods that we have, we could say we can break it down here. So you have a classical method here and the instrumental method here. So in the classical, it can be qualitative or quantitative. So qualitative, it could be a chemical test or a flame test. So it's just telling you if your what we call the material or chemical is present or not. How do they do the gun residue analysis? They add something in your hand, so that material that they add in your hand could react with some gunpowder. Okay, but right now they just swab your hand and then they look at your what we call the swab. They analyze it in the instrument and they can detect how much gunpowder residue do you have, the GPR, gunpowder residue. Okay. So quantitative analysis is either gravimetric or volumetric. Now, instrumental method, you can have spectroscopy, which is listed here, which we're going to discuss, and then the separation analysis. And then we have the electrochemical method. Okay. So this is the one that they used before. Third world countries are still using them now. This one, we are the one who lead in this development. Okay. And right now, the one that they're trying to develop is how to detect the COVID-19 virus as short as possible. Because how do they do the analysis right now? They have to swab. They put that thing in your nose, and you can see it's so long. Okay. They try to develop one using the blood, but unfortunately, it has what, 50% accuracy. So that's not really good. Because if it's a 50% accuracy, so it's just like either you have it or you don't. Okay? And it's not good in terms of analytical chemistry. So let's look at the gravimetric method. So as I have told you, gravimetric method is based on the mass. Okay? So what does this mean? if it's based on the mass, you need balance. So the way that they do gravimetric method, there are two methods. One is precipitation method. And the root word for this precipitation method, as you could see, is the formation of precipitate. So what does it mean? You have a sample, and then you add it with another chemical in the hope that the chemical that you added will react to the target sample that you have. So based on the determination of analyte, which is precipitated by a precipitating agent. So in this method, what happened? Your analyte is converted to a sparingly soluble precipitate. And what you do, you isolate this precipitate, okay, by filtering it, wash it to remove any impurities, and then convert it into a product of known composition by suitable heat treatment, and you weigh the product. Okay? So this is one way for them to determine if silver or chloride is present. Okay? So usually if they want to determine the chloride content, they react it with silver nitrate. Now the amount of the silver chloride that precipitate, they will relate it to the amount of the chloride in your given sample. So this is what we call a precipitation reaction. Okay? Now the other one, or before we go to the other one, so this is what we have. So you have a solid soluble salt containing Pb2 plus and other chemical species. And what you're going to do, you make it in a solution, okay? And then you add it with another solution, this time containing sulfate. So what happened? Lead that is present in this solution, upon reacting with the sulfate in this other solution, will form your solid lead sulfate. Now it has to be in the solution because you cannot have a chemical reaction when both of them are solid. Have you observed or experienced two solid materials when you put them together, they will react? Usually both of them are in solution form. So what you're going to do, you're going to filter and then you weigh the amount of the lead sulfate. Since you know how much of the sulfate that you have there, you can get the corresponding amount of lead in your sample. Okay? Now the other gravimetric method is what we call the volatilization method. So what do we mean volatilization method? So this is something to do with the loss of the volatile species, and this gives rise to the signal. So in this, the analyte or its decomposition products are volatilized at a suitable temperature. The volatile product is then collected and weighed, or alternatively, the mass of the product is determined indirectly from the loss in mass of the sample. How do they determine the moisture content of food? So usually you weigh the food, and then what you're going to do? You get the mass of the food, and then you heat the food. So anything that's lost there, upon eating the food, you weigh it again. So the difference between and after heating, that corresponds to the mass of the water. So that is an example of a volatilization method. Another way to do it is if you have a hydrocarbons. Okay? So if you want to determine a hydrocarbons in a given sample, you heat it. So what happened? Your hydrocarbons is converted to CO2. So anything that's left there, we could say, is the other component that is not hydrocarbons. So that's how they do volatilization. It's just involved weighing. Okay? Now, the next one that we have is volumetric method. So volumetric method, the other term that we have there is titrimetric method. I just need to get my part. So here, so why do you think we call it the Titrametric method? Because volumetric analysis is just titration. So it's commonly, it's a general term for a method in quantitative chemical analysis in which the amount of substance is determined by the measurement of the volume that the substance occupies. So it's commonly used to determine the unknown concentration of a known reactant. The volumetric method, you do titration. Okay, and titration is a lab technique in which one substance of known concentration and volume is used to react with another substance of unknown concentration. So the idea that you have there is at equivalence point, the mole of A is equals to mole of B. And usually you already know this. So what are the way to get the moles? Either moles is equals to what? Mass over molar mass. And what's the other way to get the moles? Concentration times volume. So concentration unit is what? Moles over liters. And volume would be in liters. So this becomes moles. And you all know here, this is usually the unit of what? Grams. And this is grams over moles. So if you're going to do the math there, that is equals to moles. Okay? So usually, in the volumetric method, you have what we call here the titrant, the one in your burette. And the titrant is the one that has a known concentration. So once you titrate it, you will get the corresponding volume, right? So once you have the volume and the known concentration, you can get the moles of your titrant. And usually, at equivalence point, that should be equals to the moles of your analyte, the one that you have here. Now, there are 4 common titration based on the principle that you have acid-base. The classic acid-base titration. So you can get the concentration of an acid by reacting it with a known concentration of the base. Okay? So what does this mean here? You can have the acid here or the base here, or you can have the base here in the burette and the acid in the receiving vessel. It's fine. You can also have a titration that deals on reduction oxidation, the redox titration. Okay, so all you need to know is, you know, the stoichiometric ratio, especially if it's not 1:1 ratio. Okay, example of the redox titration, the reaction of permanganate with oxalate. So you can use that. Now the complex formation titration. This is the one wherein you form a complex. And usually they use this to analyze metals, especially if it reacts with the so-called EDTA, ethylene diamine tetraacetic acid. So what happened, the metals will form a complex with the EDTA. And usually this gives you a distinct color. Okay, so when you do titration, you have to know where is the equivalence point. So the equivalence point that is the point where they have a stoichiometric ratio, either 1:1 or whatever is the stoichiometric ratio that they have. And usually, ideally, the equivalence point is near or equal the endpoint. So I don't know if you still remember the acid-base titration, what's the common indicator that you use? How do you know that you're done with the titration?
Phenolphthalein color change.
Okay, phenolphthalein color change.
Methyl
Phenolphthalein is
orange.
just one of the indicators that we use. So if you have a base here and an acid here, the true equivalence point is the first permanent light pink color. If you see the dark pink already, that means it passed through the equivalence point. Okay? So phenolphthalein is only one of the indicators, at least in the acid base. Other acid base indicators, you have what we call methyl red, methyl orange, bromthymol blue, bromcresol green. So the way that you try to look at this, these indicators, they usually have different colors at certain pH. Okay? So that's a very good way there to serve as an indicator. One best example of a natural indicators, I think, is the cabbage, the violet cabbage. It has different colors at different pH, and this is due to the presence of these so-called anthocyanins. So at different pH, it has different colors. Okay. Now redox titration, if you're using permanganate, that itself is a self-indicator. So what does it mean? If it's self-indicator, you don't need an indicator. That material will change color of its own. So usually permanganate is what? Violet. So if it reacts with oxalate, it becomes colorless. Well, it depends. If permanganate is the one that you have here and this one is colorless, so the what we call endpoint is the formation of the pink color. But if it's MnO4 that is here and you're adding C2O4, then the loss of the violet color. So you don't need an indicator there. The permanganate itself will change color. In the complex formation, where you have, like we call EDTA, you have other indicators that you use there. And then we have the so-called precipitation titration. So what does it mean? When you add your titrant to your analyte, you're going to form a precipitate. Okay? And one methods that they develop, there's a lot of methods that they develop, is this so-called argentometric titration. What do you think is the element that is involved here?
Nitrate, silver nitrate.
Okay, it's usually silver. Because the meaning of Ag there is argentum. So anytime you do a titration that involves silver, it's an argentometric titration. And that silver, titration can either be a precipitation titration if a precipitate is formed, or a complex formation if a complex is formed. So how do you differentiate the two? Precipitation, there's solid. Complex formation, usually there's no solid on it. Okay. And this is how your equivalence point would look like. This is just one data. Okay. So this is, we could say, the raw data. So this steep point here, that is your equivalence point. Now there is several ways to determine what is the equivalence point. You just use the same data. Maybe do the so-called first derivative. And when you do that, usually this value here should align with that value there. And if you're not still convinced, you can do the so-called second derivative. So as you can see, it should still be the same as the first derivative and this one. And if you're still not convinced, you can do the so-called grand plot. And the grand plot here is the difference that you have here okay, where you have how do you call it, a negative linear relationship, and then it becomes straight line. So that's the thing. So this is just one data that is processed using different methods. The raw data, okay, and then you process it, get the first derivative, and then further on you can do the second derivative, and then you can do the so-called grand plot. Now, some said classical methods is already phasing out, okay, and some have suggested that they should not be taught in classes anymore. But the thing is, what if bad case scenario, it happens that all electricity or power is out, okay? How are you going to analyze stuff? Because aside from the indicator here, you can also use like a pH meter, a voltmeter, and what you analyze here, instead of the volume here, you will have the pH, or we could say the potential, okay? But the best way that they said is using the indicator. Because usually when you do the analysis with the indicator, when you reach here, you stop. But if you use like a pH or a voltmeter, these are instruments already, you just go along. Just want to make sure you pass through the end, the equivalence point. Okay? Because I asked my friend in the industry, do you still need to do that? They said from time to time, they have to do that, just to monitor if their instrumental method is doing fine. Okay, so they still practice this thing, because instrumental method, we could say it has a lot of advantages compared to the classical methods. Okay, it's fast, you can automate it, and when you do that, sample throughput will be high. So it's a very, what we call, fast analysis. I mean, if you use instrumental method, in terms of speed of analysis, it will be fast. You can analyze more sample. Another advantage is its sensitivity. You can do trace or ultra trace analysis. Okay. So remember the example that I gave you, how Lance Armstrong, okay, was caught doping, because as time goes on, the sensitivity was improved. Okay, and then in terms of selectivity, it can it's accurate in the presence of many other components. Reproducibility, you can always analyze it, and it's giving you the same results. And the most important thing here is you just need a small amount of your sample. Okay. In voltmeter, what do you, what sugar meter, all you need to do is what? A drop of blood, and it can analyze the sugar content that it has. But it has its disadvantages. One, it's expensive. Two, some of the instruments are so complex. That's why you need to be trained to use it. So if you, what we call working on clinics or hospital, they have these so-called laboratory technicians. And usually their job is routinary analysis of samples given to them. Okay? Because their jobs there also include the maintenance of this instrument. Some instruments are what? $500,000. Okay? That's why it's usually costly and expensive to have high-end instruments. Okay? Now, how do they analyze, or how do instruments do analysis? What they do is they look at the property that is being exhibited by their target analyte. So these are just some of the stuff that they have. Radiation emission. So when I'm talking about radiation here, this is different from the so-called radioactive materials. Okay. Radiation has something to do here with light. So you have emission, absorption, scattering, refraction, diffraction. So if you're going to look at this one, so these are methods: fluorescence, phosphorescence, luminescence. So why do you say emission? So some materials, when you excite them or when they absorb light, they emit. And that emission of light that they have, you can take advantage of that to analyze the target analyte that you have in your sample. If it's absorbed, okay, you can also take advantage of that, like what they do in spectrophotometry, NMR, and the AAS. So AAS is usually the one that they use for heavy metals. Radiation emission, this is the one for materials that fluoresce. When you say fluoresce, once you put light on it, it will still glow after some time. That glowing is due to the emission of light. Now, some of them will scatter, like if it's turbid or when it has a Raman. Some of them would diffract, like the one that they use in the X-ray. So this is another way to measure heavy metals. Okay, refractometry, interferometry, it has something to do with the behavior of the molecule. They also have this rotation, like polarimetry and circular dichroism. So it has something to do with the conformation of the sample. Now you also have something to do with potential. Potentiometry, classic example, pH meter. Electric charge, coulometry, so it has something to do with the coulomb. Okay? Conductance. Electric current, voltammetry. And this amperometry is what? $1 billion industry. Why? What industry is $1 billion industry? Anyone? Maybe when we go each one of them later on, you will know what's that $1 billion industry. Okay? And even though we discussed mass in the classical, they also have to determine mass here in instrumental. Okay? Gravimetry is the main term, but here they call it electrogravimetry. So these are just some of the things. So today it's just a crash course that we have. Another way to do it is maybe this one. So whenever you have an instrument, all you need to do is, if you put a sample to it, that instrument will generate a signal. And usually the signal is proportional to the amount of the sample that is present, or to the amount of the chemical that is present. That's the main or the general idea of the use of the instrument. So what you're going to do is, you have you are interested in one chemical, and you know that that chemical would have a property that when you use that instrument, you can relate the amount of the chemical to the signal that the instrument will generate. Okay, so that's the idea of these so-called instrumental methods. Okay, so let's try to go with the electrochemical method. So usually they said if you have an electrochemical method, your sample should undergo redox reaction, or the so-called electron transfer. Now there's two main analysis here. So one is the potentiometric method and one is the voltammetric method. So if you're going to look at the root word, this is what? Potential. And this is voltage. Okay? So what do they do in the potentiometric analysis? So the analyte, so the target compound that you have is part of the galvanic cell. And it's going to generate a voltage due to a drive to thermodynamic equilibrium. So what does it mean? It will generate a signal due to difference in activity. And you can correlate that activity to concentration. And the amount of the voltage that is generated by the galvanic cell depends on the concentration of the analyte. What does the pH meter do? Anyone? Don't tell me. You say measure pH. Yes. But what does it really measure, the pH meter? What does pH means? Because you're right when you say it measures pH, but what does pH means?
Concentration of acid and bases.
Is it acids and bases or just exclusively H plus? Because pH is equals to what? Negative log H plus. So what pH meter do is really determining the concentration of H plus. Okay? So the same thing that happened in potentiometric analysis. So if the H plus is high, it will show it to you. And what you do, you convert that concentration term in the log and it will give you a reading in the form of the pH. And what do we know? The lower the pH, the higher the concentration of H plus. Another thing that they use here in potentiometric analysis is the so-called ISE, ion selective electrodes. And one classic example of ISE is the pH meter. But when you say ion selective, you have a certain ion and you just analyze it for that. Why do you think we have to analyze fluoride? What samples do we usually analyze for fluoride? Anyone? You want to determine the
Sodium chloride.
Sodium chloride. Usually, if you have water sample, you want to determine the fluoride content of that.
Oh, sorry, fluoride.
Okay,
I
fluoride.
I
Okay?
thought you said chloride.
No. Because if there's too much fluoride on that, it can give you fluoridisis, fluoridisis. It's what we call a term that is associated with diseases of too much fluoride. And you don't want your sample to have no fluoride, right? I mean your water sample. Because fluoride is needed for what? Where else you can find fluoride in your everyday material?
Toothpaste.
The toothpaste. Your mouthwash. Because you need fluoride for your dental thing. If you don't have any fluoride, your teeth will deteriorate. So one item that they have there for ion selective electrode is for fluoride. And then they also have some item that is used for biological fluids. The ammonia content, the chloride content, the calcium content, calcium ion content. Where do you think they use the calcium ion content? Anyone? What happened when we grow old?
Osteoporosis.
Osteoporosis. So what's osteoporosis there? what happened? When we grow old, we lose the calcium. The calcium that we have in our body leach out as calcium 2+. So they said if you have too much calcium, you're going to have problems in your bone because calcium would stabilize your bone. But when we grow old, it leach out. And they can detect the calcium that you have in your biological fluids. And the material that they use is an ion selective electrode. Okay, so that's the, we could say, application of potentiometric analysis. Now the voltammetric analysis, what they have here, the analyte is part of an electrolytic cell. So what you do, you let the current flows when the voltage is applied to the cell due to the participation of the analyte in a redox reaction. So what happened? The conditions of the electric cell are such that the magnitude of the current is directly proportional to the concentration of the analyte. So the way that you're going to do is you have different voltage. You apply different voltage. And then at different voltage, if your sample, okay, will undergo redox, there will be a peak that is generated. And that peak generated is in the form of the current. So the higher the concentration there, the higher is the current that you have. Okay. Now, one of the things that they have here is this so-called amperometry. And this is the basis of that so-called billion-dollar industry. Okay. So usually voltammetric analysis, they use it for metal. And if you're going to see what these materials look like, so I think some of you have seen this. If you have an aquarium, I think you use this, what we call pH meter. They are all pH meter here. Okay. This one is an ISE. This is an ISE, an ion selective electrode. Now this is the one that they use for voltammetry. Okay, we have that in PACE. I have equipment like this in the PACE in PACE University. And then this is for conductimetry. And this is the billion-dollar industry. You familiar with this? This is your billion-dollar industry. You agree with me that this is a billion-dollar industry? Huh? What is that last figure? I hope you don't have that.
Blood pressure?
Is it blood pressure? So that means you really don't have that.
Diabetes and blood pressure.
There's a glucose monitor.
That's a glucose monitor, a glucose meter. And it is based on amperometry. That's a billion-dollar industry, right? Do you agree with me that it's a billion-dollar industry?
Yes, definitely.
Especially here in the US. They said the main reason why we have high incidence in the Western world of COVID is because of our health compared to the one in Asia, where the incidence is low. If you're going to look at the incidence in Europe, most of the people who died there are what? They're old people, but they're not healthy. Okay? Although they said there are some people who died that are healthy, but if you're going to look at the general data, most of those who have died are obese. And I think it gets worse because all of us are in quarantine. That makes us more obese. We don't do exercise. Now, I mean, if you try to analyze the thing, how come the mortality rate is so high in the Western world compared, let's say, to China? Okay? The incidence that they have there in Wuhan, they said it's low because there are not a lot of old people because the city is a young city. Okay? I'm not trying to what we call, what do you call this, insulting. I'm just trying to look at the data as a scientist. Because sometimes you have to be objective. I myself is obese. Okay, so before you say anything, I myself is obese. I myself has that equipment. Okay? And that's why they said, maybe the pharma industry is doing us really like this, so they keep having money. Because if somebody said, oh, I find a material that can cure diabetes, so overnight that industry will fall, because you don't need to have to use that thing. But I'm just trying to show you that, hey, it is based on chemistry, and the way that they do it is they analyze the principle there. So if you're going to look at this, you have a blood sugar, blood that you put there. So I'm not sure if they have an enzyme or an oxygen. So there's a series of reactions that happen there, and whatever the sugar content that you have there, it will generate you a value. Okay. Right now, everything is a number. Before, it has something to do with the analog style, but now everything is, we could say, digital. But I'm just showing you here, hey, this is a product on how we do chemical analysis. Okay? So it's a $1 billion industry because a lot of people are using that. Okay? So that's just electrochemical. Now let's go with the spectroscopic method. So as I told you, it has something to do with the interaction with electromagnetic radiation or light. So most of these methods in this category are based on the measurement of the amount of light that is absorbed by the sample. So this is the so-called absorption base. And it can be atomic absorption or the so-called AAS, where you use it to analyze metal. Molecular absorption, which has the UVBs. Okay. Oh, no, the UVBs is not it because this is what we call absorption-based technique. Oh, no, UVBs here is molecular. Sorry, because I always have the atom and the molecule. So UVBs is, if you have any colored thing, it will give you some absorbance, and the NMR method. And the rest of the methods are either light emitted or scattered. So when you say light emitted, these are the emission based, like there's an atomic emission and the fluorescence. Now the scatter method, you have the so-called Raman. Okay, so if you're going to look at the methods that they have here, these are just the example. So the emission one, the gamma ray, and then you have the X-ray absorption or emission. So it tells you what is really involved there. I'm not going to go in depth on that. I'm just telling you that this methods that you have here is based on the interaction of light with matter. Matter, there's the sample that you have. Now you have the UVBs, the UV here, and the absorption. So this is what we call the colored region. So the way that they look at here, you choose one wavelength and you try to determine the concentration of a given sample there. Okay? And you do it using a standard, which I'm going to discuss later on. And then you have the IR absorption and the Raman scattering. This is the so-called vibrational spectroscopy. Okay, so these are the one that is involved. What happening to them? So usually it happens because you put light or electromagnetic radiation to your sample or the matter. So it can be this one, we could say is the absorption. So what do you have here? A light source. Then you select a certain wavelength in the monochromator, and then you have the sample, and then it will give you the detector, and then it will be converted to a readout that is understandable to you. So what I have here is still an analog. Now this has something to do with emission, okay, wherein you have a light source again, and what you do, you're going to select a certain wavelength and then put that in your sample. And what they do, as you could see, it's not directly like the one that here, because at a certain angle, you're going to determine its emission at a certain wavelength. And then there's a detector, and then there's a signal processor and readout. The last one that we have here, this is for scattering. So what you have here is you have the source and the sample side by side, and then you select the wavelength there, and then you will see the detector. Okay. So as you could see, almost all the spectroscopic method has a source. Usually it's a light source, or your what we call rich enough laser as the source of the light. Okay. Now laser, we could say is monochromatic compared to the other light source, which is polychromatic. When you say polychromatic, it is in a certain region. Laser is just at a certain region. So these are some of the instrument in spectroscopic method. This is both UVBs, so maybe you're familiar with them. Okay. Well, I think I lost something. I just try to see. Oh, the picture cannot be displayed because I know I posted a lot of picture there. Anyway, when I edit this again, the other pictures that you have here are the other spectroscopic method. You have this is for the UVBs. I have posted the fluorimeter, okay, but unfortunately it's not here. The IR and the Raman, okay. Now the next method that we have is the separation method, the chromatographic method. So the one in chromatography. So T.C. Wet, when he discovered chromatography, he stated this as a method in which the components of a mixture are separated on absorbent column in a flowing system. So what we have here is what? Plant materials that is separated in, if I'm not mistaken, I'm not sure if it's a sun or a calcium carbonate. And we're able to separate these, what we call materials, into different colors. Now, the IUPAC definition of chromatography is a physical method of separation in which the components to be separated are distributed between two phases, stationary and mobile. So if you're going to look at stationary, it's not moving. And then you have here the mobile phase that carries the sample. And once it passes through the stationary phase, the components in your sample will interact with the stationary phase, and that's where separation takes place. So it can be solid or liquid supported on a liquid or gel, that's your stationary phase, and the mobile phase can either be a gas or a liquid. And if it's a gas, you call it a GC, and if it's a liquid, you call it an LC or HPLC, which is high performance liquid chromatography. Okay, so if we're going to look at the classification of chromatography, the instrument base are here. So liquid, gas, and right now they have this supercritical fluid. Now the rest here, like TLC, paper chrome, we can say it is the classical method. Now, why is chromatography useful? Because that's the one wherein you separated all the components that you have in a given sample, and then you can quantify them. So this is the method that caught Lance Armstrong. And this is the method that they use to screen in forensic science, in food analysis or food industry. So you usually use this for everything, especially the LC. If the sample can be dissolved in any liquid solvent, HPLC can analyze it. Okay? Now for the GC, these are for samples that are volatile. So those are, we could say, the main requirement for your sample to be analyzed using this method. Okay, so usually LC and GC just separate them. What identified them, okay, even my picture here was lost. I don't know why. But if I'm going to show you, here's a picture that I have, because I usually have the slide. Here's those pictures that I have. I don't know why it's lost when we have the class already. Because maybe I removed the source where they came from. That's why. Okay. The one that I'll show you here is the GC and the HPLC that we have, because we have a forensic science program at Pace University. So we need to train the students to know them, how to use them, because those are usually the one that you have in the lab. Okay. Now, as I told you, your chromatography just separates. The one to identify each of them is either the electrochemistry or spectroscopy. But there's one that they use, is the so-called mass spec. Okay. So here, it's the analyte is ionized and subsequently detected. Although the common term spectroscopy is not really the right one. Okay, because what you have here is mass spectroscopy. So the most important use of mass spectrometer is quantitative analysis in GC and HPLC. And they have a new one that they have. This is for metal, the ICP-MS, ion coupled plasma. Okay. So if we're going to look at some of these methods, so usually this is the technique that we have, and then the theoretical principle that you have there. So these are for the classical one. Now for the instrumental one, you have here potentiometry, potential, voltammetry, current, and then you have the AAS, the molecular absorption, atomic emission. All of them is based on Beer's law that I'm going to discuss in the next slide. And then here, molecular fluorescence. Okay. Now, as I have told you, the instrument only works on the property, okay, that is being applied. Now, how you know the amount that you have? Usually the instrument cannot tell you that. What do? You do the so-called calibration curve. Okay? So as I told you, for any instrumental method used for quantitative chemical analysis, there is some functional relationship between the signal and the concentration. As I've told you, okay, this signal came from the property that the sample has and your instrument can detect. Okay, so what do you do if you want to determine the concentration? Because what the sample gives you is just a number. You can have it a signal like this, but you don't know how much is that corresponds to. So what do? You have to prepare the so-called calibration curve. So how do you do that? You have to prepare standard solution. So what is the standard solution? So this is the sample, this is the chemical that you want to analyze. So what you do, you prepare different concentration. And then you run it also, just like you run for your sample. And they will give you signal. You will have a series of calibration standards, you analyze it, and you're going to have this so-called best fit line. And from that, you'll be able to determine the concentration of your sample. So I would say for you to understand, maybe like this one. So you have your different concentration. So let's say that's what you have. Now, your sample would have a signal like here. So what you do, all you need to do is determine the equation of the line of this, which is just what? Y equals to mx plus b. You can use Excel. You plug in the x and the y. So when I say x and the y, x is the concentration, y is the signal, right? Now, once you have your sample, what you have is just the y. So all you need to do is using the equation of the line that you determine from the calibration curve, you determine X. And X is your unknown concentration or the concentration of your sample. Now, what if you have the reading of your sample here? What do you do? What do you do if your reading is here? This is usually the Beer's law that they said. So if you have your sample here, are you going to extrapolate? As much as possible, don't do it. What do? You dilute your sample. Okay? Now the calibration curve will only work if the reading of your sample is within your calibration curve. If it's higher than your calibration curve, you cannot extrapolate. Okay? Because Beer's law also has limitations, because sometimes, so let's say this is what you have in terms of concentration. Now, sometimes at higher concentration, this is the reading that it has. So what you're going to do? Are you going to get the best fit line from here going there? Or are you just going to what we call limit it until this point? Because this is the only time that they are linear. Okay? So it's always the SOP, especially if you don't have a method that is already developed. If you're just starting to use it, so all you need to do is you have your standard calibration curve and then your sample. So whenever you do the analysis, you always have a set of standard solution and your sample. And ideally, you want the reading of your sample to be within the standard solution. If it's too high, you dilute your sample. Okay? And the thing that I just discussed to you, this is the basis of the so-called assay that we have. Analyte, this is any chemical species whose amount is being determined in a quantitative analysis. So that's the one that I mentioned, the chemical that you want to analyze. That's your analyte. And assay,
So,
yes?
Professor, I have a question. For the graph that you were just showing right now, with the slope, are you saying that once it turns non-linear, we can't use it anymore as an adequate assessment?
No, I mean, you have to make sure it's linear. If it's not linear, then just limit it to the concentration where the signal is linear with respect to the concentration.
I'm sorry, say that again, just limit it to the what?
So let's say if you have it like this, a reading like this, you just limit it until here, because that's the only point wherein there's a linear relationship between the signal and the concentration. At this level, you cannot have that relationship anymore. So that's the limitations of the Beer's law.
Okay, thank you for clarifying that.
Okay. Now, they have developed this stuff already, as I have told you, in terms of the so-called assay. I don't know if you do some screening. When you go to the doctor, they ask you to do urinalysis and blood works. So what they have already there is a developed assay. So sometimes this assay uses the principles of the instruments that we have. Okay, so assay is analytical procedure in which the analyte is the ultimate target. So these are just some. So the assays that I have there, that's really what we call a reaction. And upon the reaction, they try to monitor, okay, the signal that they have at a certain wavelength. So this is already preset. You don't need to prefer the standard solution. The only time that you do it is when you calibrate your instrument. Okay? Maybe you're familiar with the word calibrate. So usually when you do calibration, usually you do it at the beginning. Okay. Even your sugar meter, you calibrate it before you use it. Okay? So when they ask you to do, when they do this bilirubin thing, so there are some instruments that's available by Hitachi, Siemens, and Vitros. So these are the reactions that they have. So what happened? When you add your sample containing with bilirubin, it contains some material there that will give you a certain color. And that certain color can be monitored at a certain wavelength. So you're doing your spectroscopic analysis, but in an assay form. Okay? Calcium. So you have Hitachi, Siemens, and Vitros. So these are the reaction that is involved there. And they would form colored material that can be monitored at a certain wavelength. So glucose, it's not the glucose meter that you have. Okay? You have those three, what we call instrument. And again, they will produce something that you can monitor a certain wavelength. It depends on the color that form. Okay? And show here, they have a control. So these controls, these are your standard solution. In some, you don't need the calibration curve. In some, they just give you like a ratio and proportion thing. But this is after they establish already the protocol. Okay? So in the assay development, as I've told you, the instrument is still there. Because the so-called stimulus, that's the property that we look. In the analyte, okay, that is analyzed by a given instrument. So you have a stimulus there, maybe light, heat, current, voltage, you put it on the sample and they try to see what signal would come out. And the thing that you need to remember, no assay is developed in isolation. Rather, assays are developed with a specific purpose in mind. So what's the ultimate assay that they want right now? Okay? They want a fast detector for COVID-19. The one that they have in the White House is what, 15 minutes? But the problem is, it's a yes or no because there's only 50% accuracy. Okay? So I don't know what Abbott will do. Abbott is the one who developed it. I know some friends who are involved on that thing and I also laugh with them. Oh, yeah, your thing is not working. Because the main protocol that they have right now is using the PCR. But it's a very sensitive method because what you do here, when you get the sample, and even if you just have one strand of the virus, it will be amplified there, okay, to detect if it's present or not. Now, the one that they try to do, the antigen for the so-called antibodies, they're still not sure if it's really working. Okay, so what do you need to remember? So this is just a series of steps when you do the chemical analysis. So whenever you try to analyze something, okay, the main objective of a chemical analysis, whether you're going to use the classical or the instrumental method, is to provide information in order to solve a problem or to make a decision. Okay? Instruments are important, but solid scientific procedure throughout the method of analysis are necessary in order to produce valid, okay, or valid results. A scientist's role in the method of analysis is more than understanding and making measurements. It doesn't mean that if you have the instrument, everything is okay. No. Okay? You still have to follow some sort of SOP, standard operating procedure. So you have to design a method of analysis appropriate to the problem. It would require experience, broad knowledge, and the problem-solving skill. And the analyst must deal with the nature and the origin of the sample, the desired accuracy and precision, and the selection of the appropriate technique. So the technique is the methods that we have discussed. And when you do analysis, sometimes you coordinate with other stuff, other material. Significant interaction with collaborating investigator are typically required, because what happened, you develop it and you don't share it to the other, okay, it's useless. And you want to make sure that it's not only your lab who develop it. If the other lab will utilize it, they would have the same results. So not only for the analyst to acquire the necessary information to solve the problem. You also have to communicate the information that can realistically be provided, given the nature of the sample and measurement techniques available. What if I tell you the one that happened, the zombie drug thing in Brooklyn, the analysis was not done here in New York. It was analyzed there in San Francisco. Why? Because there's no lab that analyzed that thing here. The only lab that they have right now is there in San Francisco. So I'm hoping that they will also develop the same protocol here in New York. Okay? So that's what it means here, communication. When the concept of quality are applied to a chemical measurement, the term quality assurance is more commonly used. So quality assurance. So you want to make sure it is really working. So quality assurance in a chemical measurement involves the action within the method of analysis that provides satisfactory measurements with appropriate confidence, high dependability, and in a cost-effective manner. So as much as possible, you want it to be affordable, right? Because that's the problem right now. At least I think the expenses in the testing for COVID is a little bit cheaper now compared before. Before, they have problems with some raw materials needed in the assay. Okay? So the steps that you usually have, you formulate the question. So this is defining the problem. You select the analytical procedure, and then you do sampling, and then sample preparation. You do analysis, you report and interpret, and then you draw conclusion. Another book would say it like this: select method, obtain a representative sample, prepare your lab sample, define the replicate sample, dissolve the sample, eliminate interferences, measure property of the analyte, calculate results, and estimates the reliability. So this is the most important part. Because if the design that you have is not good, it's just like jump in, jump out. The instrument is only useful, okay, on how you develop a plan to do the analysis. Another book says here, select method, acquire sample, process sample. Is sample soluble? If it's yes, can you measure the property? If no, then you can have to do like sample pretreatment method. Okay, so these are the things. So let's say, how are you going to analyze M&M? If you want to analyze the presence of what? Caffeine. Are the samples in M&M all the same? Some M&M has this peanut, some M&M has this coconut, some M&M has the dark chocolate. Okay, I know there's some M&M that is the jalapeno thing. So you have that to take into considerations. That's why the first step that you always do is you define the problem. What is the intent of the measurement? What's the necessary considerations in sampling and sample preparation? What's the best technique for making the measurement? And how are we going to evaluate the data? How are we going to report the result? Or do we have the resources needed to accomplish this analysis? Okay? Or maybe just to give you, these are some questions that you need to ask when you define the problem. COVID-19, how are we going to analyze it? So when you do the swabbing, so as much as possible, you keep your sample in a sterile condition. I don't know if you notice is whenever they swab, they close it right, they collect it right away and then close it because they don't want it to be contaminated. Because once it's contaminated, your results is compromised. Okay? Now, what are the things that you need to consider? The method that you choose, will it give you quality or quantitative information? So if it's going to give you quality, at what extent you want it to be a qualitative one? If it's a quantitative, you need to plan tasks associated with the sampling, sample preparation, and calibration more meticulously than a qualitative analysis. Especially if you have drug cases, right? I think the sentence, how long is your sentence, depends on how much of the grams of drugs do you have. So it's really very important because there's a case in Boston. The forensic analyst that they have there is not doing her job. You just want to make sure that the case will be what we call solved. So he said, this is present, this is not present. Okay, and when they found out, okay, she was sentenced, and all the cases that involve her has to be dropped because there was compromise. They didn't follow the protocol. So a careful consideration of the analyte, the sample, and the instrumentation are critical in the development of a valid instrumental method. So what's the properties of your sample? Because depending on that, okay, you're going to use the appropriate instrumental method properties and then the analyte properties. And what is the concentration range? Because I don't think it's useful when you only have what, ppm or ppb level and the detection limit of your instrument is ppm. So the answer is always there, not detected. Okay? And how do you do the sample preparation? Sample preparation can affect the properties of your sample and the analytes that you're looking for. So at what accuracy and precision you want it to know. And are there existing methods? Because usually, if there's existing method, you just use that method. If not, then you have to develop your own. Okay? So method modeling and plan. So you have to have an idealized representation of the complex steps of the analytical method. The problem in doing analysis is the analyte that you want, that's not the only one that is present in your sample. Okay? And those present there, those other materials present there in your sample, they can interfere with the analysis of your analyte. So that's the problem. Okay? That's why you have this step-by-step thing. You have to address here, it's necessary to perform measurements on the sample to determine its homogeneity. So what if it's not homogeneous? That's another problem. Development of the sampling plan to accurately address the goals of the method. What if your sample, when exposed to light, would lead to your analyte being what? React and produce another material. It happens to me. I'm trying to analyze an antibiotic residues in, believe it or not, SHIT sample. When I say SHIT sample, you read it what it is, okay, in animal manure. Now, what I realized, I cannot detect it. Because what happened, they undergo reaction during that time. So the form that they have is not the form that I'm looking for. Okay? So that's the thing that these steps telling us all about. Rigid method modeling and what we call planning. Okay? So here you have to follow this protocol. You don't really need to do this. Define the sample, and then what's the sample preparation that you need to do, the technique that you use. Do you need a control samples? Okay, usually you need it. These are just the standards that you have. Okay, and this is the thing. How are you going to obtain and store the sample? So I think they were successful in solving Lance Armstrong problem because they were able to store the sample. Because you can contest the storing of the sample. You know the baseball player from Milwaukee Brewers before, Ryan Braun. So he contested his urine samples in court. Okay, that something might happen between the transport from Milwaukee to Montreal, where they do the analysis, and he won. But when he got when he was sampled again, the next time they followed the correct protocol, and they found out that he's also juiced. He's also using a PET performance enhancing drugs. So you have to take into consideration the protocol here, the sampling and the sample handling, because the law or the legal team can question you on that. Okay. So the sample preparation that you need to take into consideration. The problem with the analysis, it's not that you have the sample and then you inject it right away in the instrument. That's not how it works. If you watch the CSI, that's not how it works, okay? You have to, what we call, follow protocol. It's not that you have the sample, that sample, you inject it right away. That cannot happen, okay? You have to do some sample preparation, because I told you, the one that you want is not the only one that is present. There are other stuff that are present there, and it's going to mess up your analysis. So you have to take into consideration, okay, when I do a sample preparation, do I need to keep it in the freezer? Because some of them might, if you leave it for what, several months, they might be gone. Water samples, it can only last for 6 months. Longer than that, it's useless, okay? So the way that they try to do it, like these urine samples, they frozen it, and they only remove it once they, what we could do, the analysis. So they perform this sampling, and then they perform sample analysis. So usually they use some replicates. So they just trying to, what we call, preserve the integrity of the sample, especially if this is high cases, okay? And once you have that, you're ready to perform the analysis. And usually when you form the analysis, you always use the standard, as I have told you, the importance of this so-called calibration curve, okay? And these are just some of the methods that they use. The IR, the X-ray, so elemental analysis. So it's just telling you, are they specific and what's the minimum sample size? If you're going to look at this, 5 micron, 10 micrograms, so it's really small. Okay, and then you have here the IR, some of the stuff, and there are a lot. Okay, now the question that I would ask, how are you going to analyze the tap water that we have? Are you ready to determine what you have in your tap water? So I'm going to show you here. Not that one. So you type your own zip code. So this is my zip code. Do you see the what we call thing there? And then you can look at there, and it can tell you what contaminants do you have. So in my zip code here, it says here, there's 16 total contaminants. The question is, do you want to know it in the first place or not? Okay, and then it will tell you what it has and which one exceed the regulation. So it takes them a while to develop this what we call database. Okay? Because I told you, if you're going to analytical chemistry, nothing is safe if you're going to look at it. So once I make this present, the PowerPoint, you can click the link there and maybe type your own what we call zip code, and you will find the thing. So there's one here, haloacetic acid. So this is a very what we call timely thing. If you're fond of boiling water, right? Once you boil it, you use it and then throw it. Don't reuse it and boil it again, because you're going to have some halotanes that forms there. Why? You have what? Chlorine. So when you hit it, there could be some reaction there. And then if you reheat it, there will be another reaction and you're going to produce other stuff. Right now, we might not be able to see it, but remember, DDT was supposed to be a wonder drug before, and then they found out it's harmful. Okay? So that's one advice that I can give you. Once you boil water, you just use it once. And then if you want to have another boiled water, throw it, use another new water that you came from the faucet. Because those are those things, the total trihalomethanes, those are the stuff that you have there. Those are the reactions that happen when they react with fluorine and chlorine. That's the one that they use for treatment. Okay? So I think this is because I'm trying to show it to you so that you can, what we call, explain it to your students. Because what we have right now is we lack scientific culture. Okay? And the classic example is the COVID-19 that is happening with us. You have to tell people that we need to wear the mask. And the other things that they have right now, the problem that we have is the so-called microplastics. They're still trying to develop a method to do that. But they said right now, all materials around us is made up of what? Plastics. So what's the end point here? It will go to the water, and sometimes all the food that we have, they also contains the so-called microplastics. Okay? And then I like to show you this case, the Theranos case. So what's the idea that they have here? So she was dubbed as what we call the next Steve Jobs. Because the main thing with the Theranos, the meaning of the Theranos is therapeutic diagnostic. So the idea that they have there is with just the drop of the blood, they can tell right away what's the composition of your blood. Okay, so instead of using this sample, all you need is this sample. Now, right now, I could say in paper, it is, we could say 5 to 10 years ahead. Maybe in 5 to 10 years, this is possible. So what does Elizabeth Holmes want to do? That in every Walgreens, they have this diagnostic thing. All you need to do, okay, you put some amount of your blood and it can tell you the amount of whatever you want to see in your blood. But they found out that's not true. Because I think some people who use it, they have a high reading of some of the stuff that they have in the blood. And they got so scared and went to the doctor right away. And from, I think he was able to start fund around billions. And he had some people who invested in him. Right now, he had a court case against her about this Theranos case. Now, the 5 take-home message that I like you to what we call take with you, because you will be in the forefront in this scientific culture that we have, is everything is made of chemicals. Water is a chemical. Okay? I remember some non-scientists mentioned that if you cannot pronounce the name, you don't have to eat it. Okay? Ascorbic acid, maybe it's not new to you, but that's just vitamin C. Okay? There are vitamins whose name is like what we call tocopherol, They are not familiar to you, but they're good. Okay? So let's drop the connotation that chemicals are bad, because everything around us is made up of chemicals, as simple as the water. And then whenever you look at this, what we call toxic materials, to tell you frankly, it's the dosage that makes the poison. Even water, if you take too much water, you can die. There's an incident, I think maybe around 2010, when the we is what we called new. So a radio station conduct this contest, water to win we. So the winner who won died after 2 days because he drank too much water. Okay, it just happened that there are some chemicals that are toxic even at low dosage, but any chemicals that is taken in excess can be toxic, right? Anything that they accept, they said is toxic. So it's always the dose that makes the poison. Okay, and then I don't know if you're going to get mad at me with this one. There's no difference in the so-called natural or synthetic versions of a chemical. Maybe those who are fond of this so-called organic stuff, I tell you right away, they're just crap, okay? Because if you say organic stuff, what are you putting there? You put there the poop of the animal as fertilizer, right? Now, I can tell you, because my PhD is about poop, that's why I told you the SHIT sample, okay? So these animals that you have, they injected it with antibiotics to make them grow faster. Now, unfortunately, not all of the antibiotics stay in the body. Most of them go out in the form of poop. So if you're going to use those poop as your fertilizer for your organic stuff, you are introducing some antibiotics there. Okay? To tell you, your body will not tell you if the source comes from the lab or the natural one. If you take ascorbic acid, it will not tell you, I'll take you because you came from citrus. No, I'm not going to take you because you came from a tablet. Okay? Because I can assure you, those synthetic stuff, they have quality control there to make sure that there are no other toxic chemicals that they have there. Because sometimes it's more practical to synthesize them than, let's say, if you want a perfume, for a drop of the perfume, you have to have what? A track of rose petals for you to get that drop of perfume when you can do it in the lab the easier way. Okay? There's no difference between what we call the natural or synthetic version. So I think the one that hit me is the organic people. The thing is, the organic people, it's more expensive, but it's not even, it's safe. Because I study about these antibiotics in the animals, okay? And then the so-called natural chemicals are not automatically good and artificial chemicals are not automatically bad. So I think it's related to that, okay? You can die from eating cassava if there are what we call cyanide in cassava, okay? And what happened during this news in the Caribbean? Many people died from drinking wine or alcoholic drinks. And they found out what? Instead of ethanol, they have methanol. They're both alcohol. But all I can tell you, not alcohol are good. The only one that you can drink is ethanol. The rest, don't drink it. Okay, the isopropyl alcohol that you use, don't drink it. That's not. It's only ethanol. That is what we call, that's good. And ethanol can come from fruits or you can prepare it artificially. And the last thing, a chemical's property are determined by the other chemicals that is bound to. So sodium on its elemental state is very reactive. You put it in water, it's going to react. But sodium attached with chlorine to give you sodium chloride has a very different property, okay, as the sodium. So the property of the what we call materials depends on its nature. So if it's we could say one thing that is, we could say, toxic on its own, it can be safe when it is attached covalently or it's chemically attached to another material. Because the options that they have here with the anti-vaccine, there is a material that they use there in vaccination that contains mercury. Yes, mercury is toxic, okay? But the one that they use in the vaccine, I'm gonna say thimerosal or some sort of that, it's an ethyl mercury. So in that case, the mercury is attached to another element. So in that case, the toxic property is not exhibited. And they found out that if it goes inside your body, it remains in that form. So the dangerous part is if you're going to detach the mercury out of it. Okay? So I would like you to ask the education on how you can register so you can get to the Blackboard. I will email the requirements the latest later today. So you already know the first two: develop your own big or great ideas, whatever's your teaching, and then develop 2 teaching materials using the strategies that we discussed in class. And then the third one, which is today, find some chemical that you're interested and report on how this chemical material is being analyzed. Again, you can use this as example in your teaching. Okay? So everything that you're going to submit to me, I want you to use it when you teach your course. Oh, there you go again, the sound. It was every 1 minute during the peak season. I'm just singing Another One Bites the Dust. Okay. So thank you very much, because this is my last meeting, and unfortunately, we still don't have the Blackboard. That's why in our meeting last time, Dimo said, do you think we're going to be paid for this? Because we don't have the CRM. So this time, okay. So please ask the education what you need to, because we already told them the Blackboard is available. So it's your turn to enlist the student. And Sishan, sorry, I just saw that the email ad that Craig gave us is different with you. So I just got the email ad today. Okay, so my apology, and I think Demos didn't realize it.
Thank you so much.
Okay,
no problem.
But all my Zoom recording will be available in the Blackboard. So including this one. So this is just my 3rd recording. So you missed Demos all recordings just in case. Okay, so thank you very much. Do you have any question? I think somebody.
Professor, did I will get the email regarding this?
Which one? No, I have not sent that thing yet about the requirements, but your classmate knows about the first.
No, after that, I will receive the email.
Yeah, definitely, because I already have your email ad. So I can include you in the email ad.
Thank you.
Yeah, because there's another student attached to your name.
Okay, thank you so much.
And when Craig said me, no wonder he is asking for this course. And I told myself, and you didn't even bother to tell us that there's some student that's missing. So question. So I hope this is not the last time that we're going to see each other. I mean, if you need help in your what we call teaching, if I can be of help, I'm more than willing to help you. And Dr. Chang will be the one that will be teaching you on Thursday. I think it's still the same time, because it's going to be an overload for him. He's teaching every Monday and Wednesday. So we will have now Monday, Tuesday, Wednesday, Thursday. Every day is now teaching. Okay? So question?
All right, Professor. No, just want to say thank you.
Okay.
Appreciate it.
Thank you very much. So I hope you learned something. Okay, if you have any questions, feel free to email me. Okay?
Thank you, Professor. Thank you.
More than likely, I will be doing that.
Thank you.
Thank you, Professor.
Bye.
Bye, everyone. Stay safe.
Bye-bye. Have a great day.
You too. Always what we call gloomy day.
Yes. Bye-bye. All right.